Hello, my name is Grant Meyer. I am a junior mechanical engineering major here at the University of Nebraska-Lincoln, and I'm also the team lead for the UNL Husker Rocketry team. So for a little background on what we do, we build and construct model rockets for a yearly competition. And depending on what that competition may be, that is going to affect what kind of level of motor we're going to end up using in our final design. You see, the way model rockets motors are classified is by their level. So in order to fly a larger, more powerful rocket motor, you need a higher level of certification. So for a smaller rocket, you don't need a high level certification. So this year, our competition is going to be at Spaceport America Cup in Las Cruces, New Mexico. They are a high power competition with a lot of different universities that go there. Typically, it's about 200 universities get selected. Typically have a 100,000 to a 30,000 foot high different category. And you have an option with the payload challenge. So this year's payload challenge is to get the best recording from it. For the rocket, how we designed it, we use a software that will simulate and model the rocket called OpenRocket. And this is used heavily in our design. Whenever we make a modification to our rocket, whenever we think of an idea, we're going to use OpenRocket to simulate the trajectory of the rocket, how high it's going to go, the velocity of it, and its acceleration. So for our initial design, we were going to use a carbon fiber wrap, a dead reckoning tracker payload, so that it was going to actually track the rocket where it was going to go without using any kind of GPS. We were going to have a GPS inside of it just to double check and just be safe, just so that we don't lose the rocket altogether in the desert. And so here in this little diagram, this is actually the initial plan of the whole project. So you can see here at A, the rocket takes off at launch velocity of about 83 feet per second. And once it reaches about 10,500 feet, it has a delay about 1.5 seconds. And then the drogue parachute is going to come out. And then our payload is going to eject from it and be attached to a parachute and slowly descend. And as it's descending, on the bottom of the screen, we have the red box with the purple wave coming out of it. And that's kind of there to symbolize it tracking the rocket using radio waves and dead reckoning. And so as the rocket is descending at D and E, the main chute is going to deploy at an altitude of 1,000 feet above the ground. And this slows the rocket's descent rate to roughly 22.8 feet per second. And when it touches down, then we're able to go on our phone and then go and try to find the rocket using the dead reckoning chip. But this kind of had a problem with our whole design and the process we were going to go about it. So our main issues with it is that our construction site was totally unavailable throughout the whole year, from first semester and second semester. And that was because the ventilated rooms inside of our university's paint room were under construction due to outdoor construction, and it would be blocked, and also senior design projects for other clubs and other classes. They kind of took up the whole paint room, so we couldn't use the university's paint room. We did try reaching out to the College of Architecture, seeing if we use their paint room for epoxying the rocket and painting it, but they declined our kind of proposal to use their facility because that's only for architecture. Another issue with our design was that dead reckoning is not unattainable, but it's very difficult to attain from the same measure. And so it's very difficult to pair those both together. And so our solutions for that was to just strip the payload. There's no payload in the rocket. So the diagram that was before this slide, that was cut off. And we went to an alternate location, which is this shipping crate, which is used by another test team in the aerospace club called 100K, where they do a lot of different tests for their motor. And we were allowed to use their site at the airport in order to do the epoxying and make sure all the components would fit together and would have a nice place to cure over time. And another solution was to purchase the components instead of using carbon fiber and manufacturing our own tubes, because we wouldn't have the time if we try to wait for the paint room to allow us to use it because they're still under construction right now. And so let's left us with two very important tasks. The first task was to get the avionics bay working, and the other task was to have a successful ejection charge test before the launch. And so in order for our avionics bay to get working, we had to have our altimeters to be programmed, and the trackers needed to be able to send and receive data. And so these two videos I have here, let me just move my head around the screen. This video I'm going to play is the avionics bay, and there's going to be a Christmas light attached to it. That's going to basically be replacing our ejection charge in our aerospace lab, because we can't use an ejection charge in there because we don't want to start like a fire or just have any like debris going around the room. So we use a Christmas light, and when the Christmas light turns on, that symbolizes the ejection charge going off because electricity is going through it. Like that. All right, there we go. That was the light symboling the ejection charge going off. And if you read on the computer, or there you can see the altitude going up to its apogee, and then when it's coming down, so when the velocity gets negative, that's when the light turned on. And so we got that to be successful. And then the next thing on the list was to have our ejection charge test also be successful. And we were able to do that with using about between 5 to 6 grams of black powder for the ejection charge testing. And that would separate the main and drogue chute from the rocket. And we have the little test video here. Ready? Oh, yeah. And that was the ejection charge test going successfully, which is how your parachutes deploy about 10,000 feet and then 1,000 feet above the ground. Ready. And so here is our avionics bay and our open rocket simulation. So on the, make my head there big again. All right. So on the top left of this screen, we have all electronic components, and this is how we got all of the altimeters and trackers synced up together using 2 batteries that would also be connected together, and they would turn on when you put a key in it and then switched it. And on the bottom, we have our open rocket design for competition, and overall, it's about a little over 10 feet in length, and has a diameter of 6 inches. And you can see all the little components in here where we had everything. So on the back, we have the motor, which is in gray. And then we have our drogue parachute right in the middle. And then you have our shot cord, our avionics bay. And then we have our main chute, and then the other shot cord connected to the avionics bay. And so here's the designs of the rocket right here. And here's the actual rocket that was created. And so the avionics bay area, here it is on the left with all of the wires attached, all the batteries, and is connected to our key switch, which comes out of the fiberglass tube in this picture. And on the right, you can also see where the key switch is up in the upper middle portion of our red body tube. And so here is how the key switch kind of worked. And that was how everything would turn on. It was all soldered and attached together correctly. And so using the Christmas light test again, when it went up to apogee, the drogue chute would come out. And then as it would descend to 1,000 feet, then the main chute would come out using the Christmas light test again. And here's a simulation using an open rocket for how our rocket flight, velocity, and acceleration would go. So the rocket on this graph, it shows it to be about 3,250 feet above the ground, or excuse me, 3,250 meters above the ground, which is roughly about 10,600 feet above ground. And as it slowly comes down, you can see where our main parachute eventually opens, which creates this nice linear line. And it slows down to a descent rate of about 25 miles per hour. So still pretty fast, but definitely way slower than if we didn't have our main parachutes, and it's way safer that way. So lessons learned and our current progress about this. We learned that a lot of stuff changes. We did not expect to not be able to use the university's paint room. We did not expect for us to not to find a provider for the dead reckoning ship to use our initial design. And so this kind of made us realize that we have to verify design concepts first and early on throughout the year. And for our current progress right now, we do have a possible launch in Minnesota on April 30th. If our launch is successful, then we are all set for the Spaceport America Cup competition on June 20th. And that lasts for about a week, so from June 20th to June 25th. And then we have the extra days to come back from Las Cruces, New Mexico, back to Lincoln, Nebraska. And so if you have any questions or comments about this presentation, you can email me at gmeyer7@huskers.unl.edu, or you can email our aerospace team at aerospace/rocketry@unl.edu. Thanks for watching.